thank you everyone. Hopefully everyone can hear me just fine. So talk today, I'm a lecturer at the University of Edinburgh, of course, and I am in the Institute of Energy Systems. It's been a very long week, sorry. I'm still here, we'll see how much. And today I'd like to talk to you about my research, and putting it in very broad terms, this is looking inside of an operating engine. And the engines of interest, what we're interested in, are automobile engines. So you look at these, and if you take one out of an engine, it can look just like this, and you say, why do you actually want to look inside there? I'm not sure. And actually, when taking out the car, saying, how are you going to look inside there? I guess let's concentrate first on the why. And if you remember back to thermodynamics, it's a piston cylinder device, so we have several of these in here, and I'm just looking at the engine cycle through here. So we have an intake where we suck air down into the engine, and we compress that air and fuel mixture, and we ignite it, and this is when we convert the chemical energy of the fuel into heat, and this is then converted to work. So if you remember back from your thermodynamic days, or if you're in my class taking thermodynamics, look at the PV diagram and you say, oh yeah, these processes, 1, 2, 3, and 4, we're interested in the work out. This is the work that's turning your wheels, making you go. The expense of this is the heat from the combustion, and what we're interested in doing is always maximizing your work, maximizing your efficiency, which is what you want over what you pay for. This is what you want, this is what you pay for. Now what's not shown on this is what also we don't want, and this is, pollution, soot. We don't want that. And so in order to understand the efficiency and the emission production, we have to look inside of the engine and figure out what's going on. So we're interested in the science of the engine. So let's go ahead and take our production-like engine, and this is exactly what we want. We want to be able to look inside each of these cylinders and figure out what's going on to understand how can we make this more efficient and how can we make this less pollutant. So here I'm going to show a video to kind of take the spotlight off me. I know this is supposed to be a TED-style talk where you're supposed to concentrate on me instead of what's behind me. We're going to take a little bit break. And here is just a video. So the casing and everything of the engine is almost completely transparent. You can see it. We're just looking inside. Here you see the pistons moving up and down in their respective cylinders. You see the valves opening and closing. And the cylinders themselves are also transparent. This is essentially exactly what we want to do. So this is an example of an inline 4, so you see 4 cylinders. And what we're interested in is just concentrating on one cylinder, which we're going to do now. And as I mentioned, we want to look at the processes going on inside. So here you're actually seeing the intake flow going into the engine, compressing it. Then you're igniting it. Boom. This is providing the power, and it's turning your wheels, and then the emissions and everything go out through the exhaust, just like that. You also can see the fuel injection up here. There's fuel right there. As the inlet valves open, the fuel and the air come in together, and so you have roughly a homogeneous mixture. And this is what you're compressing. And you have a spark plug that's igniting it, and this is how you're getting your power out. And then if you put in the all the other components and say, oh, that's actually how it looks in an engine. Now you see all 4 cylinders firing, and essentially this is exactly what we want to study, but we want to simplify the problem. We just want to concentrate on one of these. And the question still remains, but how are you going to make this transparent? And it's really hard. So what we're going to do is take our production-like style geometry engine, and remember we want to look inside, but remember also we want to just look into one cylinder. And the way we can do that is a single cylinder optically accessible engine. So here's an example of that. It looks much different. Essentially, this is a picture of the engine actually operating when it's fired. And so if you just take a normal camera, the exposure time is much too slow to capture everything that's covering. So here you kind of see a glowing. This is probably the combustion from many, many cycles within the engine. What's key about this is you have a quartz glass cylinder liner. This can either be the full length of the cylinder or the majority. This is about the majority. So you can look right inside to the cylinder and see what's going on. Also, if you look at the piston, right now this is for very simple geometry. This is a flat piston, but it is also made out of glass. You see it's surrounded by metal, but you can look directly through the piston. So if you look from underneath, you can look and see what's going on. So far, essentially, if you stand right in front of the engine and look with your own two eyes, you can see what's going on. The problem, again, is your eyes are much too slow to actually see what's going on inside of the engine. So what we want to do, actually, is use laser diagnostics and optical diagnostics to actually measure and understand the science inside the engine, what's going on. So here's an example. We have a laser, which comes out as a laser beam, which shows here, and goes through some optics, and we have a mirror underneath the engine, and so this remains still, and the piston moves up and down, and we create a laser sheet. So we use some cylindrical lenses, and we broaden the sheet, and so this has usually a thickness of 1 to 2 millimeters, maybe even less, and you can take a high-speed camera and view, or a camera with a very short exposure time, and view exactly and capture everything what's going on inside the engine. So let me make this cartoon here more of a reality. Whoops. If we look at this, here's an example experimental setup. So lasers actually they're bouncing through many mirrors and lenses coming from this direction. It's actually going into this 45-degree mirror underneath and is going up. And right now you see it illuminating everything within the engine. Well, yeah, it is, but in fact it's actually a very, very thin light sheet going in there, and as it hits the top of the cylinder, you'll have some reflections, and that's why it looks like it's illuminating everything. But using this high-speed camera, we're able to capture everything, or what we want to measure, on a certain plane within the engine. Okay, so what are some things that we want to measure? And remember, we're interested in making this thing more efficient and less pollutant. One of the key aspects is the flow itself within the engine. There's a technique called particle image velocimetry. With this, you actually here's an example. This is just a very generic situation here. We have a laser, we're creating a laser sheet, a light sheet, and we put particles within the flow field. These particles can be oil droplets, or they can be solid particles like titanium boride, or titanium oxide, and essentially here's our camera, just represented by a little dot, and we're able to take images of these particles, and we take them at a certain time t, and we also take an image at just a little bit afterwards at time delta t. However, these particles are not going to be in the same position. They have now moved, because if you have a flow, particles are now moving. So essentially, you have two correlated pictures of the particles moving around. So you're measuring the distance. If you know the distance and you know the time separation between these two, you have a velocity. And here you look at different parts, different little interrogation windows. So here is an interrogation window. And you look at how multiple droplets within this interrogation window move. And so you get the average velocity of these multiple particles. So here's an example looking into the engine. So here is the intake valve. This is open, so the flow is coming into the engine, as what we saw in that animation. And we're just looking on a very, very thin sheet right in the center of the combustion chamber. And I means inlet valves, E means exhaust valves. And here's an image of these particles. This is silicon oil. within there, within the engine coming in, and if I flip between two images, you might be able to see that the particles are moving. And if you use a very sophisticated algorithm to understand, okay, yes, this particle was this particle in the beginning, then you're able to correlate these and get a velocity field. Here you see the velocity coming into the engine, high velocities coming in, and you're making this clockwise kind of tumble motion, and it's called tumble flow, within the engine. What the goal here is to create high kinetic energy within the flow, and this kinetic energy will then kind of dissipate down to the turbulence scales, and this allows your flame to propagate faster. If your combustion and your flame propagation is fast, your efficiency goes up. And now if you change the geometry of your engine, this flow can change dramatically. And so this is what we're interested in looking at. So let me give an example. Here I'm going to show a movie of the flow throughout an entire cycle. And here we're not going to deal with combustion. We just want to look what's the fluid mechanics in and out of the engine without any combustion. So here, this movie is compiled of 720 images, velocity images. That means we have 2 images per every one of these. So in actuality, we have 1,440 images. And this is taken within 150 microseconds. And so we have 2 images every 208 microseconds. So this is, in fact, a high-speed camera. And you also need 2 laser pulses for each one of these. So it's running at 9.6 kilohertz. So yeah, very fast. And so here you go. Here, starting with the intake, the inlet valve is shown right here, kind of coming in. You see the high velocities coming in, creating this clockwise tumble motion. Here we have reflection, so we're not getting the flow. The velocity kind of dies down. The piston kind of comes up and compresses the flow and creates a little bit of turbulence when the flow interacts with the walls. This is when we would have combustion, but we don't have combustion for this cycle. Here now the exhaust valve starts opening. What you saw there was kind of the blowdown process because the pressure in the exhaust port here is greater than what it was in the intake or within the engine, and the process repeats itself for the next cycle. So all this, now you get to look at the fine details of the flow. You're able to kind of stop it, look at it, and evaluate it. All this, remember, occurs, and this is at 800 RPM. This is considered a very low engine speed. All this, 720 images, occurs in 150 microseconds. So this is why we call it high-speed imaging and quantitative information to understand the flow. Okay, let's look at another case. Remember how I showed in this illustration or the simulation, the fuel injection was outside of the engine? Now we're interested in putting the fuel injection, putting it at high pressure inside the engine. And this is where we have potential to have fuel savings of 60% or a little bit more for a given operating condition. So here, now we're zoomed in, looking in the engine. We're still looking at a single plane. What you see here, these are the droplets within the engine, silicon oil. This is a spark plug. And so this is a center electrode and a ground electrode. And you have a large voltage drop between these two, creating ions to run from one electrode to another. And this creates a spark. And this ignites your mixture. So if we have fuel and air within here, that's going to ignite your mixture. But here, we actually don't have fuel and air in here yet. We only have air in there. What we're going to do, there's a high pressure injector right here, and we're going to inject fuel right at the spark plug, and then we're going to ignite this fuel directly afterwards. 2 things you're going to see. These are silicon oil droplets. As the flame comes, you're going to see a very dark spot and a flame propagate through here. The flame is consuming the silicon oil droplets, and this is how we can identify where the flame is. And it'll appear dark because this camera is detecting just natural light. And the flame comes out first as UV, so it doesn't detect this. Then you're going to see some real combustion luminosity, and what you're going to see is actually soot. This is going to be very bright, and this is visible light, and so you're going to see the detection of this. So here, there's a fuel injection. You see the spark. There's the flame, kind of this dark region, and then here, this is the combustion. This is the soot. Now this is not as sooty as the image that I showed with this diesel engine and all this black soot coming out, but this is still something that we don't want. So we have the potential to improve the fuel economy by up to 60% at this given engine operating condition. Shoot, we kind of fail on the emissions production side. So you hit one and you kind of miss the other. So still work needs to be done. Here's another situation. We're going to have the same thing, but you're going to see no flame propagation. You actually start to see a flame a little bit, and then, shoot, nothing happened. And so essentially say, okay, well here we met the soot category, that's for sure, but you got nothing out of it. And so this is not quite ready. This is still in the research phases and saying, all right, we want to clean this up and we want to avoid this. And so how to study this further. Now what we need to do is understand what the fuel distribution is along with the velocity inside the engine. So here you can use another technique, which is called laser-induced fluorescence. So we're not introducing extra particles within the engine, but we're introducing a certain fuel or certain molecule within the fuel within the engine, and you use a laser light at a certain frequency, and these molecules actually absorb this light and they get excited, right? And these molecules go from a ground state up to an excited state, and then they go back down. And as they go back down, they're going to fluoresce, they're going to glow. You put a camera that detects this glowing, essentially, and you can understand what the fuel distribution is right next to the spark plug, and understand, when the fuel moves away too fast in here for a certain fuel, this is why we're not firing. You incorporate this with the velocity as well, and you say, when we put the jet in a certain configuration, or if we improve the injector, we won't have the situation where we don't ignite. If we're able to improve the mixing, then we're not going to get the soot problem anymore. Okay, so that's essentially what we're trying to do. Now let's ask the question again, why? Human impact on climate change. I think it's very evident. And sorry, I do have bullet points on here, but I think it's good to make a point. We understand that the fossil fuels right now, they're roughly about 82% of the world's total energy demand. Here's an example. This is the Department of Energy Outlook in 2012, and looks at this is looking at the carbon dioxide emissions from different forms of energy: residential, commercial, industrial, transportation, and electrical power. Transportation, and the color scale shows different forms. Brown is petroleum, green is natural gas, black is coal, and blue is electricity. If you see here, transportation, it's about 98% petroleum right now. Now, we do have hybrids that are helping this. We do have electric vehicles that are for sure helping this, but also the electric vehicles, depending on where you are in the world, okay, if this is coming from the electric power, a lot of it's coming from coal. And so we have to keep in mind, just because we're not making any pollutants out on the road, you're also firing these coal power plants, essentially. And we have to recognize that the improvements through combustion science do make a big impact. This is actually the quickest way to reduce the CO2 and soot within the air. So to illustrate this example, here's a picture of Los Angeles in 1970. You can barely see the skyline. It's actually awful, right? Okay, we recognized this in 1970. I wasn't there, so I'll say they recognized it in 1970. And let's take a look at what Los Angeles looks like today. It's much cleaner. We have more cars on the road today than we did in 1970. And these cars are actually larger, yet they're getting better fuel economy and they're cleaner. So these improvements through the combustion science community is making a big impact. And let's not forget electric vehicles and hybrid vehicles. They are very significant. And here is another graph from the Department of Energy. We have two curves here, actually four curves, one with one with diamonds. Here's a diamond one, and the diamond one's hard to distinguish there. and we have squares. Diamonds mean when we have, this is the total energy, and squares means energy from petroleum. Light blue means this is when our batteries are very cheap and when they're very efficient. And the darker blue means take the batteries out, or they are what they are today. What you see here is that these squares, they're not going down to zero within the future. And this is actually a very conservative, this is the most proactive outlook of this time. So the squares are not going down to zero, meaning that the petroleum we are dependent on the petroleum, and we are dependent on gasoline, and in fact they're starting to increase. And so so almost all projections are showing that the transportation sector is going to have fossil fuels in there. So let's be practical here. If they're going to be around for a while, let's improve them and let's make them cleaner. Let's even take a look at the markets that are out there today, things like China and India. These are growing really, really fast. Any improvements that we can make now, they're going to lead to a huge difference. So as much as we like to avoid the problem, it's not just going to go away. And this is what my research is, and hopefully trying to improve and clean up the systems. So that's it. Thank you very much, and turn over to the next speaker.
This production is brought to you by the University of Edinburgh.